So, with that, tonight's speaker is a Royal Society University Research Fellow, permanent member of staff in the School of Mathematical Sciences at the University of Southampton. He's published in fields ranging from experimental polymer physics to theoretical astrophysics. His research focuses on classical general relativity and gravitational wave science, where he's made many contributions to the theoretical understanding of relativistic motion and binary mechanics. I managed to say that without fluffing it. He's a member of the LISA consortium, a network of about 1,000 scientists involved in the LISA mission, and he leads the consortium's ongoing efforts to develop theoretical models of extreme mass ratio in spirals. Please welcome Dr. Adam Pound.
First, can you hear me? Yes? Good. Okay, thanks William for the kind introduction, and thanks for the opportunity to speak here. I was not expecting this many people. I didn't realize there were so many people in all of southern England interested in Okay, I'm going to have to actually stand pretty close to this because I have quite a few animations that I'll need to activate by clicking on here, but hopefully it won't obstruct this view too much. Okay, so the subject of this talk is, as you see, when stars fall into black holes, although I'm also going to be interested in when black holes fall into bigger black holes. And I'm going to try to connect the subject to kind of a fundamental tenet of general relativity you might have heard of before, called the equivalence principle. So hopefully it will make sense by the end. Okay, the general context is gravitational wave astronomy. I think you heard an entire talk about this in December. Hopefully I'll cover it from a slightly different perspective, although I should have asked Ian to see his slides to make sure that's the case. But it won't be too bad if you see two talks on gravitational wave astronomy. So we'll start off with just a general discussion of the current trends in astronomy, what the new face of astronomy is. Then we'll get into kind of the core topics I'm interested in: black holes, gravitational waves, and the equivalence principle. And then finally, I will talk about what is actually the main subject of my research, which is a particular class of black hole binaries that we hope to detect in the next stage of gravitational wave astronomy. Okay. So of course we all know that regular astronomy has enabled us to see pretty spectacular things. This is an image from the Hubble telescope, 25 years old now. And everyone loves these images. It's just crazy to think that this kind of stuff is somewhere out there in the universe. But it's fairly limited in what it can see. So we see a lot of exciting different phenomena in the universe with traditional astronomical instruments. But a lot of the most dramatic things in the universe actually cannot be seen with these instruments. So the main thing that can't be seen is regions of strong gravity. So all the traditional astronomical instruments are electromagnetic instruments. So they're detecting visible light or infrared or microwave emissions from astrophysical systems. And those kinds of things, first off, really strong curved regions of space-time, like black holes, do not produce that kind of emission, so you just can't see it at all with the kinds of images. But also, that kind of radiation, electromagnetic radiation, gets scattered by things in its way. So if there's a cloud of dust that will disrupt the passage of these electromagnetic waves, anything in its way will scatter it and distort it, and we won't be able to see things that are kind of cloaked behind other things. So what's wrong with not being able to see these regions of strong gravity is that it means we can't really test general relativity. So you've probably heard many times that general relativity is one of the fundamental theories of modern physics. We have the IT graphic. Well, this is good stuff. Yeah, so you've probably heard many times that general relativity is one of the two fundamental theories of the universe that we have. So one is general relativity, the other is quantum physics. But unlike quantum physics, general relativity has not been very well tested. Almost all the tests we have of it are in particular kinds of systems like the solar system, where gravity is pretty weak and objects are moving around pretty slowly. So until very, very recently, we haven't actually had good proof that general relativity is a correct theory of gravity in regions of strong gravitational fields. There we go. So because we can't see these regions of strong gravitational fields with electromagnetic instruments, that means we can't see many of the most dramatic predictions of Einstein's theory of general relativity, such as black holes. So let's have a look at something we can see with electromagnetic instruments. So this is actually real footage of stars at the center of our galaxy. So our galaxy is gigantic, it has trillions of stars in it. Here you see, I don't know, a few dozen stars right in the center of the galaxy. And if you look closely, you'll see it looks like they're orbiting around something. You see it gets kicked there. It looks like they're orbiting around something. And we can make that clearer by cleaning up the image and just drawing the orbits of these stars. So these are the orbits of 3 of those stars we saw. And you see this nice looking ellipse going around. This one is another nice ellipse, and another nice ellipse. And they all seem to be orbiting something right in the middle there. So this kind of evidence over the last 30, 40 years has made people think that at the center of our galaxy lies a supermassive black hole. It weighs about 1 million times as much as our sun. So it weighs 1 million times as much, but it's physically about the same size as our sun, because black holes are so dense. So we don't have a theory of what else that could be. Something so tiny and so dense to create these kinds of orbits around it, and it's something dark, we just can't see it. So the suspicion is that there's a supermassive black hole right there at the center of our galaxy. And the mainstream thinking now is that there's black holes like this, up to billions of times as massive as our sun, at the centers of most galaxies. They're kind of like the nucleus inside the middle of a galaxy. Well, this is very indirect evidence of the existence of black holes and the behavior of things around them. This is a bit more direct evidence. So you might have seen this in the news last year. This is an image from the Event Horizon telescope. So this is looking much, much, much more closely at one of these black holes. This is not the black hole at the center of our galaxy. This is a black hole at the center of a neighboring galaxy, M87. And what you're actually seeing here, or at least what we think you're seeing here, is light that comes from behind the black hole, curves around on the top or the bottom of the black hole, and comes towards us where we see it. And then this thing in here is the shadow of the black hole. So this will make more sense once I describe a bit more about general relativity. But even though this is a really terrific image that caused a lot of excitement about black holes and about physics, it's still pretty scientifically limited. So this is, in principle, a test of GR in strong gravity. We're seeing light in a very, very strong region of gravity. But using these methods, we can only see very, very close on the scale of the universe, very close, supermassive black holes. So with this particular instrument, the Event Horizon telescope, they haven't even yet been able to generate an image of the black hole at the center of our galaxy. This is the only one we've been able to generate an image of. And probably the bigger problem with it is that the data is really dominated by astrophysical uncertainties. So this light gets generated by hot plasma going around the black hole. and we don't really understand the physics of that plasma very well. So there's really huge uncertainties in this image, which means we can't really test GR very precisely with it because the astrophysical uncertainties are so much bigger than the uncertainties we're looking for in GR. Okay, so what can we use to test GR very, very precisely? That is gravitational wave astronomy. So this is the new tool in astronomy. And it really started 4 years ago when this instrument LIGO, the Laser Interferometer Ground-Based Observatory, made the first direct detection of gravitational waves. So unlike electromagnetic instruments where we actually can just see an image, here we don't directly see an image. We see just a certain response in the instrument, and I'll explain what's causing this response a bit later. And then from that response in the instrument, we reconstruct what must have caused the gravitational wave came out of this system and caused these oscillations in our instrument. So in this case, we were able to infer that this is two black holes going around each other. Each one is about 30 times the mass of our sun. As they go around, they spiral in closer and closer together, eventually merge, and then kind of oscillate for a little while, generating this last little bit. It's called the ring down. So this was a huge, huge breakthrough in science. The people who led the LIGO project won the Nobel Prize a couple of years later. And it's not, unlike the Event Horizon Telescope, this is not a one-off thing. This is an ongoing thing where we'll keep seeing more and more systems. So we see quite a few systems. Each one of these waves represents an observation of one of those black hole binary systems. The ones I just showed you was just from the first two, what's called science runs of the LIGO instrument. But you can actually go and check on the public website what the latest alerts are. So every time they think they might have seen a physical signal, they create a public alert, and you can actually look at what the alerts are. So the most recent one was at 1:58 this morning, and their best guess is that it's another one of these binary black hole systems. Okay, so that's just a whirlwind tour of how astronomy is progressing in modern times. Now I want to go through the physics to explain what it is I was talking about. How is it that we see the light coming around from the back of the black hole? What are these gravitational waves? And then I want to connect it to this fundamental tenet in general relativity called the equivalence principle. Okay, so the key idea of general relativity, this is Einstein's real genius idea, is that gravity is a manifestation of curved geometry. So in general relativity, you collect up all the points in time and space. All those collected points of events form a smooth shape called space-time. This is every single possible event in the history of every single possible universe. So this space-time has a particular shape, and gravity is just a manifestation of that shape. So a common way to think of this is with this rubber sheet analogy. If you have a massive object, you drop it on your rubber sheet, the massive object deforms the sheet, and then if you look at how objects move around, well, they fall down to this little pool to hit the star at the center there. If you instead, say, give this a little kick in this direction, well, then you kind of intuit that it's going to go in an orbit around and around this star. So this is like the orbit of the Earth around the Sun. The little ball that just fell directly in is as if, you fell out of an airplane and fell towards the Earth. So this isn't really a precise mathematical way of thinking of space-time geometry, but it gives you a pretty good understanding of why gravity is a manifestation, or how it can be a manifestation of geometry itself. Okay, but when I showed them those animations, it might have seemed a little bit arbitrary. So we were just working with physical intuition for what paths those little balls would follow. But the paths they'll follow is actually determined by the equivalence principle. So depending how many talks you've heard or how much you've read about general relativity, you might have seen lots of different descriptions of the equivalence principle. Lots of even actual working scientists say they have no idea what Einstein meant when he said the equivalence principle. There's so many different ways of thinking about it. But the version I'm working with here is this idea that you have a freely falling observer. So you might not be able to see. This is a little astronaut sitting out there outside the sun, just freely floating around. A freely falling observer measures exactly the same things as an observer who's moving at a constant velocity in perfectly flat, empty space-time. So just think of an astronaut up in a spaceship in a movie. They're just floating around. Even if they're orbiting around the Earth, they're just floating. They don't feel as if anything particular is happening. If they make a local measurement, they get exactly the same value as if they were just in ordinary, completely empty, flat space-time. So this is one version of the equivalence principle, that physics in curved space-time, you have a small enough physical laboratory, should reduce to exactly what you get in flat space-time. Now, one of the things is true in flat space-time is that any freely moving particle moves on a straight line. So imagine you're just out in perfectly empty space, nothing around, and you just, throw a ball in one direction. That ball is just going to keep moving forever in this straight line with the same velocity forever to the end of time. Now, how does that generalize to curved space-time? Well, in curved space-time, all freely moving particles move on the closest thing that we have to a straight line, which is called a geodesic. So let's just show this little animation. So here, this astronaut is falling into the sun, and then this ball was going around. Now, at this stage here, the astronaut sees the ball, makes a local measurement. But what does he measure? There we go. Well, if we zoom in on this little patch of space-time where this astronaut is, so this is just zooming in, well, this patch looks perfectly flat as long as you're looking at a small enough region. So any smooth shape, if you've got a sufficiently small region, is going to look flat. And in that little region, he looks as if he's following a perfectly straight line, just as he would in flat space-time. And this ball that's going around also looks like it's following a perfectly straight line in this little region. Now, when we say that geodesics are the closest thing that we can get to a straight line in curved space-time, I mean, it's a technical requirement that I don't want to get into, but the key idea is really just this. If you zoom in close, this line going in there looks like a straight line, and this line going around also looks like a straight line. So you might have wondered, say I set this ball loose right here, a couple animations ago, or the astronaut himself. Why did he follow this line in, rather than just zipping around in some crazy direction on this surface? Well, that is the equivalence principle. So locally, he has to be moving on a straight line in small patches of space-time, and when you glue all those together, what you get is a geodesic. So each of these curves I've drawn on the surface, the ones going in and the ones going around, are actually particular geodesic curves. So this is really a core idea in general relativity. That's really telling objects how they should move in a gravitational field or in a curved space-time. Okay, so if we continue this rubber sheet analogy, how do we describe a black hole? Well, a black hole is just a hole in space-time. So rather than meaning some minimum, it just goes down forever. And it's black because once something has fallen sufficiently far in, it can never get back out, no matter how hard it tries. It can accelerate as much as it wants, it can use as much energy as it wants, it's never going to be able to get back out. And that includes light. Light can never escape once it's gone in. So that's why the object appears black, because normally you see things because light bounces off something, comes back and hits you, but nothing is bouncing off the interior of the black hole, it just keeps going in and it's lost forever. Now let's go back to this image of what we think is a black hole, and this kind of corona around it. So before I was describing, you let a ball loose, or you let an astronaut loose, or you throw something, but the curvature of space-time affects everything, including light itself. So the path of light is distorted by the curvature of space-time. And so what we're seeing here is actually light that came from behind the black hole, came over the top, and came towards us. So say this is the black hole, and here we are out here taking our measurements. If you shoot a beam of light in this direction from here, it gets curved around the black hole and comes over here. Similarly, you shoot this beam of light in this direction, it's curved towards us, we see it there. You can even have things like this, where it's going towards the black hole, zips around the black hole, and then comes back out, and you see it again. So what we are seeing is the pattern formed by all this light coming from the other side of the black hole, getting curved around the black hole, and meeting us on Earth over here. So we don't see the black hole itself, we don't see anything coming out of the black hole, we see stuff coming from behind the black hole. Or some of this is actually also just a little disk in front of the black hole, but that doesn't form kind of this broad shape. Okay, so let's go back to what we were talking about before, where we had two black holes going around each other. If you're sitting pretty close to the black holes, this is just a numerical simulation, this is not observations. So you're pretty close to two black holes going around each other, and you have perfect vision of the stars behind them. These stars are all perfectly stationary relative to you. And because the curved space-time changes the direction of light, as these things go around each other, everything's getting pretty wildly distorted. So again, all these stars are just behind the black holes, perfectly stationary, not moving, but it looks as if they're moving pretty wildly, and that is just because the light is getting bent around the two black holes as it comes towards us. Okay, so that's how things look locally, pretty near one of these black hole binary systems. But how do we connect this back to gravitational waves? Well, for that we need to go further away. So here we're ignoring the details of the space-time near the two black holes, and just looking at what is the bigger effect far away of these two things spinning around each other. And what you see is it's these ripples coming out, propagating out forever, and eventually that is what we detect as a gravitational wave. It's these ripples in the space-time itself. So say we are quite far away from that binary black hole system. How do we actually detect these gravitational waves? Let's consider just a ring of freely moving particles. So remember, freely moving particles means particles that are moving on geodesics, which are the closest thing we can get to a straight line in space-time. So in this picture, the gravitational wave is coming out of the screen towards us and passing through this ring of particles. And you see as the gravitational wave passes through, the ring gets stretched, shrunk, stretched, shrunk, stretched, shrunk, over and over again. So this is the signature of a gravitational wave, and this motion is what we detect with our gravitational wave detectors. Now let me move on to the last topic, which is black hole binaries, and the specific ones I'm going to be interested in, that we'll be able to see in the next stages of gravitational astronomy. Okay, let's start with what we see right now. So this is just a picture of one of those black hole binaries. Down here is one of the LIGO detectors. The LIGO detector has these two long arms, and what we measure is the stretching and shrinking of these two arms as the gravitational wave passes through it. So this gravitational wave propagates out, propagates through the universe. Unlike electromagnetic waves, it doesn't get distorted by things it passes through, it just passes right on through. And eventually reaches us down here and stretches and shrinks these legs of this detector. Okay, what kinds of binaries can these detectors on Earth detect? Well, they're all pretty similar to each other right now. So they're all either black holes or neutron stars. Neutron stars are the second densest objects in the universe after black holes. And there are particular kinds of black holes called stellar black holes. So a stellar black hole is just one that's formed of a gravitational collapse of a regular star. Which means kind of the biggest ones we can see are maybe 100 times as massive as our sun. That's already pretty huge on the scale of stellar black holes. And neutron stars tend to only be up to maybe 3 times as heavy as our sun. So the reason we can only see these particular kinds of binaries is that down on Earth there's too much gravitational noise just from things shifting around in the Earth itself. And that means there's a kind of a low frequency cutoff in what you can see. And that means there's a cutoff, for technical reasons, there's a cutoff in how large a mass you're able to see in these binaries. So because we're only able to see binaries of certain masses, that means we're not going to really see binaries in which one mass is much bigger than the other, because they all have to be pretty big for us to see them at all. So the lighter one is going to be at least a few times as heavy as our sun, and the bigger one is going to be no more than, say, 100 times as heavy as our sun. And they tend to be going around in very, very circular orbits, and this is indicating the spin of each of the black holes, this arrow with the arrow going around it. It's indicating the spin of this black hole around its internal axis. And in these systems, the spins tend to be almost exactly aligned. So these are kind of quite uniform systems. They're going around in circles, they're spinning around axes that are either exactly parallel with each other or exactly anti-parallel. And we see maybe a few thousand cycles at most, that's quite optimistic, a few thousand cycles of these things going around before they collapse into each other and form a new object. Okay. But from that, we can still get quite a bit of information. We can infer the population of stellar black holes. So if you haven't read a lot of science lately, this is not a great audience to say that, but most people are not aware that we now think there's tons of black holes out in the universe. Tons and tons and tons of them. So, for example, in that galactic core I showed you where there's a few stars going around, a huge black hole, we expect there to be thousands of smaller stellar black holes in a fairly small region around the galactic core. And that's every galaxy, and there's trillions of galaxies. And the observations we've made so far, we've already learned quite a lot about what the typical masses are for these kinds of black hole systems. We can also learn things not about gravity specifically, but about neutron stars, which are the other common types of objects that form these systems. And so the equation of state here just means what is its internal composition. So that's probably still the long-running mystery in astrophysics. It remains somewhat poorly understood what actually is a neutron star composed of. You'd think, based on the name, it's composed of neutrons, and it largely is, but significantly more complicated than that. And the final thing we can infer from these waves that we detect is any possible tiny violations of general relativity. So far, we haven't detected any. So far, general relativity has worked exactly as we expect, and has perfectly described these systems. Okay, but to learn all of this stuff, it's not like you can just point the telescope at something and see these systems and learn all this information about them. You actually have to have a very accurate theoretical model describing the systems in order to say, well, we observed this waveform, where did it come from? What system created it? And so each system has kind of a unique signature that it leaves in the waveforms. And to determine what a waveform came from, we need a very accurate theoretical model. Even more than that, most of the time, even to detect a waveform, we need a very accurate theoretical model. Because unlike the image I showed of the first LIGO detection, where you could clearly see these oscillations just standing above all the numerical or all the instrumental noise, usually that's not the case. Usually the signals are buried under instrumental noise, and you need to dig the signals out. In order to find them, you need these accurate models. Now this is what we've done with just current instruments, which are LIGO in America and Virgo in Italy. There's actually two LIGO detectors in Virgo. GEO was never precise enough to measure anything. It was never actually designed with the expectation of measuring anything. It was just a test technology. So for the last few years, LIGO and Virgo have been making measurements and detecting these systems. As of last week, a Japanese detector, Cadra, came online. It's currently not as sensitive as LIGO, but should eventually be just as sensitive. And so we're building this network of detectors all across the Earth. Within about 10 years, we expect another one to be in India, LIGO India. So this is all within the next 10 years. Maybe within the next 10 to 20 years, we'll also have next generation ground-based detectors. So there's already funded improvements to the LIGO detectors. It will significantly increase the sensitivity. But then there's also much more ambitious things like the Einstein telescope that will be somewhere in Europe and that England is heavily involved in. And then in America, there's plans for something called the Cosmic Explorer, which will have 40-kilometer long arms buried underground. But then, really the big breakthrough will not be from all these new detectors on Earth, it'll be from going into space. So in space, there are two planned detectors. DeSiGo is a Japanese one that is not yet funded. LISA, the Laser Interferometer Space Antenna, is funded by the European Space Agency, and is currently scheduled to launch in 2032. So once you have this huge array of detectors, both on ground and in space, we're going to see a lot of more types of systems. We're going to see them much more precisely, and we're going to see them much further away. So what we've seen so far is just the tip of the iceberg. We're going to be seeing a lot of new stuff over the next 20 years. And the one thing that has been the focus of my career is these particular systems called extreme mass ratio inspirals, or MREs. So these cannot be detected by ground-based detectors, so it's very, very unlikely that they would be. But they're going to be key sources for that space antenna, LISA. So these systems, unlike the ones that LIGO sees, where you have two black holes that are basically the same size as each other, in this case, you have a supermassive black hole at the center of a galaxy, so say 1 million times heavier than our sun. And then you have a much, much smaller object going around. So this is going to be almost certainly another black hole or another neutron star. Sorry, another black hole or just a neutron star. And what's special about these systems is that this object, as it's going in towards the big black hole, spends hundreds of thousands of very intricate orbits very, very, very close to the big black hole. I'll give you a sense of the scale of what I mean in a second. So because it's spending such a long time near the big black hole, and because its orbit is very, very complicated, so it's really sampling all the space-time around the big black hole, it's an unparalleled probe of that strong field region around the black hole. So much, much more precise probe than, for example, the Einstein telescope, the Event Horizon telescope. Much, much more precise than that, and much more precise than the current kinds of measurements we have coming from the comparable mass black hole giants. So the waveforms that come out of these systems are going to be very, very complex, because the orbit that generates them is very complex. I'll show you that in a second. And as I said, they're very, very long-lived. So because of that, they contain a huge amount of information that we're hoping to be able to extract. But the signals they produce are very, very weak. So I said that oftentimes the instrumental noise is stronger than the signal itself. That's going to be especially true for these systems, MREs, where the signal is going to be roughly 10 times smaller than the instrumental noise. So it's really buried in there deep. And the only way we can ever hope to extract it is by very, very precisely modeling every single little oscillation over this huge amount of time, and that way we can dig it out from the noise. So for that, we need a very, very highly accurate theoretical model, even to find them, but then especially if we want to really learn a lot of science from them, and in particular, learn a lot about what is the real environment very, very close to that big black hole. Okay, so I said the orbits are very intricate, very complex, and that you're very, very close to the big black hole. This gives you a sense of scale. So this is just a snapshot from that movie I showed you right at the beginning, where these are the stars moving around the big black hole at the center of the galaxy. And from that, you didn't really have a sense of scale. You might have thought that the big black hole was, roughly the size of one of these dots. But no, way, 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 way smaller than that. It's much smaller than what you can see on the screen. So this is just zooming in on the tiny, tiny little region here. And this is what the MRE looks like in that tiny little region. This is the smaller object zipping around for hundreds of thousands of orbits, very, very close to this supermassive black hole. So all of these hundreds of thousands of orbits are hundreds or thousands of times closer to the big black hole than those stars were, even at their closest approach that I showed you. So this is really, really close. And as you see, it's really, really detailed. So it's a very precise probe of space-time around that big black hole. Okay, let's say we are able to detect these systems. And let's say we modeled them really, really accurately, and we're able to infer things about the systems themselves from the waveform. Well, what do we actually learn from that? So the first thing to note is that in general relativity, there's this very special feature that all black holes share a unique common form. Every single black hole out there in space, unless it's doing something really violent like colliding with another black hole, they all look exactly the same. They have a unique form. But that's particular to general relativity. If you have some other theory of gravity, the black hole will look different. So with these measurements that we get from these extreme mass ratio wind spirals, we can actually test whether these heavy dark objects in the galactic cores, so we know they're super heavy just based on how things move around them, and we know they're dark because we can't see them. We can test whether these really are black holes or some other dark, mysterious object. People have conjectures of what they might be. They're all pretty exotic conjectures. So they're probably black holes, but we need to actually assess this. And also, we'll be able to assess whether they have this very unique form that Einstein's theory predicts. So it could be that they really are black holes, but they just are black holes in a different theory, and general relativity is not the right theory of strong gravity. So with these measurements from these MREs, we'll get tests of this fact, along with many, many other tests of general relativity that are far more precise than any other planned experiment. So typically, the precision is 10 times more precise than any other planned experiment. So we get some really incredibly precise information. Okay, what does any of this have to do with the equivalence principle? So remember I said that the equivalence principle tells an object how to move in a curved spacetime. But really the equivalence principle is an approximation. It's applying to an object that is sufficiently small and sufficiently light that it's not screwing up the spacetime around it. But a real physical object will always create some small correction. So it's going to slightly deform the spacetime around it. And this small correction to the spacetime is going to alter the motion of this smaller object, and we say it exerts a self-force on it, because it's a force created by the correction that the object itself produced in the spacetime. So in other words, the motion of this small object around this black hole is not going to be a geodesic, it's going to be deviating away from a geodesic due to this self-force. And that is actually what drives the in-spiral. So the smaller object is zipping around doing these complicated orbits, but the whole time it's falling closer and closer towards the black hole. That is only true because of this self-force. If you didn't have the self-force, it would just keep going around forever for eternity. So in order to model those systems, what we really need to have a very, very precise handle on is what are the corrections to the equivalence principle. These very, very tiny corrections. So this is true for every single object you see around you. This is not unique to a small black hole or a small star going around a big black hole. Every object experiences a self-force, because every single object is slightly disturbing space-time around it. And that slight disturbance to the space-time then reacts back on the object itself and moves it away from geodesic motion. But usually, it's so tiny we just couldn't care less about it. So for example, if you have an astronaut orbiting around the Earth, the self-force on that astronaut will be roughly 1/trillionth of 1/trillionth of his or her weight. So small you could never ever possibly hope to measure. But in these MREs, not only do we hope to measure this tiny, tiny correction, we have to be able to predict what it is in order to even find the waveform buried underneath the noise. And the reason why it's important for these systems is because even though it's tiny, tiny, tiny for, say, one orbit, we have so many of these orbits, hundreds of thousands of them, that it gradually, its effects gradually build up, build up, build up. So it has a tiny effect in one orbit, tiny effect second orbit, tiny effect third orbit. Once you add up all those tiny effects, you get something that's not tiny anymore. So, just to summarize here, to detect one of these systems and to extract information about a supermassive black hole in the center of a galaxy, we need to very, very accurately model this really tiny correction to the equivalence principle. We need to do it for every single orbit with potentially millions of these incredibly intricate orbits around the big black hole. Okay, so let's say you could do that. What would the final system look like? Something like this. This noise you hear is actually the frequency of the physical waveform coming out of this system, just converted into sound waves. Now, it looked like the black hole at the center was getting bigger and bigger and bigger. It's just an illusion. The video is just zooming in closer and closer. So that's what we're trying to model. This video was created with a very crude model. This is not going to be good enough to actually detect these things. But the physical picture looks basically like that. And even once we have the very accurate model, it'll still look basically like that. Okay, so I think that is the end. So I'll just wrap up with some concluding remarks. I'm not too far over time. Okay, so we're in a new era of astronomy now, the era of gravitational wave astronomy. And for the first time, we can now precisely probe physics in regions of very strong gravity, so particularly regions containing black holes. Once we have that next generation array of detectors, both on ground and in outer space, we're going to see a lot more things. We're going to see the gravitational waves from a lot more things. We're going to see them much more precisely, and we're going to see them much further away. So we can see further and further away in space, and you probably know that means we can see further and further back in time. And these MRIs that I talked about, in particular, will be incredibly precise probes of these supermassive black holes that we have very good reason to believe reside in most galactic cores. But to detect them and to extract information from a waveform that we do detect, we're going to need incredibly accurate calculations of these tiny corrections to the equivalence principle. So these systems really allow us to probe kind of the fundamental, one of the most fundamental aspects of general relativity, which is this equivalence principle. Right? Thank you for your time.
Dr. Adam, thank you for a fascinating talk. I just thought I got to grips with what gravitational wave astronomy was, and suddenly this whole new field of it developing, just producing hopefully so much more depth and scale of information. So yeah, no, we certainly haven't duplicated anything previously. I think it's built very nicely on the previous talks we've had around the subject. So we'll have to put you to come back once Lisa's live and go through.
I'll be retired by then.
Oh, there's no escape. We have emeritus professors and all sorts. So we're going to take a break fairly shortly for people to go to the bar and come back and have a question and answer. Before we do that, question, it's a short sentence or two ending in a question mark, not lasting more than 30 seconds. Anything longer than that is an opinion. You ask questions, the speaker gives an opinion. We've got uprated batteries in the microphone now, so if you go over your length, you'll just simply get electrocuted. With that in mind, you'll have the first question. Well, the other thing is, if you use the microphone to hold it like a torch, shine it at your mouth, then we'll hear better.
Thanks very much for your talk. Can I ask, please, I'm very interested to know how you can separate the self-force from what I would imagine is a gravitational drag between the two bodies.
So, you don't have a drag if it's just a geodesic. said, it just moves around forever, eternally going around in this complicated orbit, never spiraling in, whereas a drag force would remove energy from it. You can think of the self force as an interaction between smaller objects' gravitational field and the ambient gravitational field of the big objects. So in that sense, you could interpret it as a drag force coming from the interaction of the two things.
I was thinking of the sort of tidal raising forces that you get from the moon on the Earth. You know,
Tidal forces. So you do get tidal forces, but because these objects are so dense, the tidal force is quite small. So what I didn't explain is how we actually do any of this, but there's a certain way of counting how significant different effects will be. You have a first order effect, the dominant self force effect, and there you do have additional effects coming from the spin of the small object, coupling to the tides of the external gravitational field. Then, one order beyond that, you have what you're probably thinking of, which is interaction of the object's finite size with the tidal field in its neighborhood. So that's kind of sub-leading in the counting. For certain systems, we may need to include that. So, I said we were expecting the smaller object to almost certainly be a black hole or a neutron star. The one exception to that is if we're very, very lucky, you'll see one of these things at the center of our galaxy. And that is quite close, so then it's much louder. And in that case, you can see lighter stars, like dwarf stars, so brown dwarfs or white dwarfs. And they're not so dense. So then this tidal force will be more significant because they're just bigger. So that might be a case where you wouldn't.
Thank you.
Interesting.
With this self force and these EMRIs, the models seem to show that I would expect it still to be roughly planar or whatever. It seems to be jumping around all over the place.
So that's not an effect of the self force. That's true even for G-music going around a spinning black hole. So that is somehow the shortest, or the most close to a straight line you can get, going around a spinning black hole. So
it's not like a planetary thing, then it causes it to go all over.
So you can find particular orbits that do get stuck in a plane. So if the big black hole's spin axis is like this, so it's spinning around like this, if the smaller object is going around that axis perfectly, then it will stay going around that axis perfectly. It's not going to come in and out of the plane. But if you kick it downwards a bit, then the spin of the black hole is actually going to drag it back up. And then it's going to move up and down, up and down, up and down.
Thanks for the talk. Previous talks in this series have described accretion disks around black holes. Do they influence the model and the way that the in-spiral happens?
So there's two different kinds of galaxies, or galactic cores. There's most of them, which are pretty empty in a small region around the central black hole. Even if there's an accretion disk, it's kind of further out, whereas these emeries are really tight in. Then there's things called active galactic nuclei, where there's all kinds of stuff feeding onto the black hole and often shooting off in superpowered jets. All the stuff kind of gets twisted up by the spin of the black hole and shot upwards. We are not going to see emeries in those kinds of galactic cores because there's too much stuff going on and it's going to mess up our model. If there's an accretion disk relatively close but it's not having that much violent stuff going on, then your model still might work without accounting for the accretion disk, depending on the orbit of the smaller object. So if the object is confined to a plane, then it's going to be in the accretion disk a lot of the time, and then the accretion disk is going to screw up your model. But if it's coming in and out of the plane, it only spends a very, very small amount of time passing through the accretion disk. And then it's a very tiny effect on your model.
Thank you.
Questions?
Because we're not absolutely...
Hang on a second, just wait for the microphone.
Oh, yeah, okay. It's just that because we're... Is it on?
Yes, hold it close.
All right. Because we're not absolutely sure, or 100% sure, that these objects actually are black holes, is there any sort of idea as to what they could actually be if they're not black holes?
So the other ideas are pretty far-fetched things. Well, you mentioned black holes. These used to be far-fetched. One idea is something called a boson star. So a boson is something like the Higgs boson you might have heard of, a particular kind of particle. And it's this theorized kind of star that's just a cloud, a very, very, very dense cloud of bosons. They don't interact with the electromagnetic fields around them, so they stay dark. But there's no known bosonic field that could actually form a star like that. So it's very hypothetical. There's other things called Gravis stars, which is even more arbitrary seeming, where you just have a shell, a super thin shell of matter, but nothing inside. Which sounds very, very contrived to me. I don't know if anybody thinks that's likely to exist. Those are the two main conjectures. There's also the possibility that it's really something very, very close to a black hole, but that our idea of black holes isn't quite right. So there are ideas coming from string theory, which is not my forte, so don't quote me on any of this. There are ideas that black holes are really fundamentally quantum objects. They're like kind of a superposition of quantum states in string theory. And then in this kind of description, you don't have a real black hole because stuff that goes in might eventually come out. But it's probably going to be so much later that for all intents and purposes, it's basically a black hole. But this kind of description can have really, really, really tiny effects near what's called the event horizon, the point of no return in a black hole. And if you change things around the event horizon even by a little tiny amount, that can still have pretty significant effects on the waveform that comes out. So some people are optimistic that we can actually test these quantum ideas of black holes using these kinds of systems. I should say the actual string theorists at Southampton are not among those who think that's realistic. But it's an idea.
Okay, thank you.
In the Emery situation, when the smaller object is approaching the event horizon, that means our view of the time passing on that object is eventually going to come to a stop. So what information, I'm not quite sure, I don't understand what goes on here.
So from our perspective, it'll look like it's staying there longer than it is from its perspective. As long as it comes back out, we'll still see it come back out.
But you're going to need a lot of rotations to get the information in the first place.
Yeah, so even though this is quite tightly bound, it's not that close to the event horizon that we would really get a wildly distorted sense of time. So, I mean, when we make our predictions, what we're predicting is exactly what we would see out here. So the waveform looks like whatever it looks like. From the perspective of someone riding on a little black hole going around a big black hole, the sense of time might be wildly different.
Hi. Thanks for the talk. You referred to the magnitude of your signals with respect to the magnitude of the noise in the instrument system, and you requiring extremely precise models in order to extract that signal. But if it's effectively like a white noise that you're trying to winkle a signal out, surely in a true white noise state you could extract any pattern you want. So you may be illusional that you're seeing the actual signals you think you're looking for.
So,
You see what I mean?
so the noise tends to be pretty close to what's called Gaussian noise. The way we extract these signals is with a method called matched filtering. I don't know if you're familiar with that. The idea is, say you've got some signal buried doing particular oscillations, and then you have noise that's just completely random around that. What you do is you take your prediction for what signals should be, and you have actually store millions and millions and millions of these different signals, because you've got to look for all of them in the data. So you run through this series of millions of different predictions, and each one, what you do is you integrate it against the entire data stream. And what that means is that the random oscillations that are in the noise, when you integrate your prediction against that, you get zero, because the oscillations in your signal, or your predicted signal, are just canceling out each other. Whereas when you integrate your prediction against the true hidden signal, once you've found the right one, it's actually going to accumulate with time as you integrate along your data stream. So it builds up more and more of what's called an integrated signal to noise.
So that would be per predicted signal.
Yeah, so your signal needs to match what's in there, otherwise it's not going to accumulate like this. There's a kind of deep problem that can arise, which is sometimes you can have two signals from different sources that look quite similar, and then you might misidentify which one it is. And you know, have different effects that might give rise to the same distortion of the signal, and again, you might misidentify things. So the more precisely you can measure things, the more you're able to distinguish between these different kinds of effects. And for example, for Emery signals, they have such a unique signature, it's almost impossible for anything else to mimic them. And all these different effects that can occur to them, like say you have some violation of general relativity, or you have some change of what the central object is near the black hole horizon, or say you have these little effects from accretion disks. All of these tend to have actually distinguishable effects on the waveform. So you can actually isolate what is causing what effect. But it's true that with current observations, you do often see very large uncertainties in certain measurements, and that's because of this. There's kind of degeneracy in the parameter space.
Question over here?
You talk about this self-gravitational effect. Do you mean non-linearities where superposition of the two gravitational bodies doesn't apply? Is that? And the second question is this chaotic behaviour that you're getting here? Would that make the signal interpretation more difficult to be more scaled?
So it is a nonlinear effect, and most of my research actually focuses on even more nonlinear corrections that are like products of the self force with itself almost. So yeah, this is a nonlinear effect. Chaos is unlikely to arise if you just consider the self force. People have looked into possible chaos due to that effect I mentioned, where the spin of the small object can interact with the curvature around it to exert a force on the small object. that, in certain situations, can lead to chaotic behavior. But it tends to be in such a small subset of systems that it's kind of irrelevant. And often because it's a dissipative system that's losing energy with time, you'll kind of go through it and onto something else. There's actually a lot of interesting transient things that happen in these systems. One is you have resonant phenomena, where you get, over a short time, you get a very significant qualitative change in the dynamics. But because the system is evolving, you're losing energy, your parameters are changing with time, that only happens for a certain amount of time, and you come on the other side, and then you're back to normal.
Another question.
So, on the non-linearity side of things, is there any other experiment anywhere anybody's ever looked at non-linearity or plans to look at non-linearity effects of gravitational waves?
So, the kinds of systems that we currently detect are infinitely nonlinear. So the simulations I showed you, the two black holes interacting with each other, coming together and colliding and forming a new black hole, those are simulated using what's called numerical relativity. You're taking the Einstein equations, defining the equations for general relativity, and you're solving them on a big computer. And you're solving them as exactly as you can, so exactly up to numerical error in your code. And that is infinitely nonlinear systems. Einstein equations they have infinite powers of the variable you're trying to solve for. So the systems that I'm describing, MRIs, are actually much less nonlinear. Or they're nonlinear in different ways. So they're fully nonlinear in terms of the effect of the big black hole. They're only mildly nonlinear in terms of the small self-force effect of the small black hole.
Right, I think that's all. Good point to round up tonight. Once again, Adam, thank you very much for fascinating talk and some quite lively discussions as well. We'll be back here on Monday the 6th of April, exploring the language of text with Anne Ratner. And please give Adam another big round of applause.
Oh.